Welcome to the Explainer. Today, we are taking a deep dive into an absolutely fascinating mystery sitting right at the bleeding edge of blockchain technology. We're going to investigate a massive, highly anticipated network upgrade that promises to completely revolutionize smart contract performance. But, and here's the kicker, it harbors a hidden, strict hardware restriction that has honestly left a lot of developers completely stunned.
Imagine this. You're a developer, right? You write a perfectly clean, mathematically sound smart contract in Rust. It compiles flawlessly on your machine. But the moment you try to deploy it to this blazing fast new network, it gets instantly rejected. Just a hard failure. Now, you might be wondering, why? Why would a multi-billion-dollar decentralized network intentionally ban basic math functions that your laptop literally uses every single second of the day? Well, that's exactly the mystery we're solving today.
So here is our roadmap to crack this case. We'll start with the Arbitrum Stylus promise, then meet the FPU gambler, look at the strict determinism mandate, uncover the Stylus WASM restriction, and finally, check out the ALU surveyor solution.
Okay, let's dive right into this. Section 1, the Arbitrum Stylus promise.
For years, the Ethereum virtual machine, the EVM, has been the gold standard in crypto. But it's got some serious bottlenecks, like this heavy 256-bit word overhead that makes complex math super slow and really expensive. Enter Arbitrum Stylus. This upgrade introduces a secondary WebAssembly, or WASM virtual machine. And this is a huge deal, because WASM maps cleanly to actual computer hardware. We're talking near-native execution speeds. Plus, it lets traditional developers write in languages they already know, like Rust, C, and C++.
Because this WASM upgrade is an order of magnitude faster and significantly cheaper, it suddenly unlocked capabilities that were just impossible on-chain before. Devs started dreaming big. They envisioned complex, multidimensional automated market makers, advanced cryptography like ED25519 signature verification, and crazy high-level math using polar coordinates and continuous curves. Think of the stuff pioneered by projects like OrbSwap. The potential felt absolutely limitless, but as they pushed the envelope with all this heavy math, they hit a massive, invisible wall.
Which brings us to Section 2, meet the FPU gambler. To understand that invisible wall, we physically have to look inside the processors running these networks.
Inside your computer chip, there are basically two ways to process math. First, you have the arithmetic logic unit. Let's call it the ALU surveyor. It deals in exact, undeniable whole integers. 1 plus 1 is exactly 2. It's perfect, but sometimes a bit slow. Then there's the floating point unit, or the FPU gambler. This thing processes continuous decimals blisteringly fast. But the catch? It doesn't actually calculate the exact answer. It uses proprietary hardware secrets to frantically throw darts at a board, giving you a really good but inherently lossy guess.
This guessing game creates a one-way street. To put it simply, it's like a giant blender. You know exactly what fruits you tossed in, but you can never, ever perfectly reverse engineer that smoothie back into the original apples and bananas. When non-deterministic hardware guesses math based on trade secrets, the exact data path is destroyed. It's constantly out there rounding off microscopic fractions just to make the numbers fit into its memory.
So, moving on to Section 3, the strict determinism mandate. Let's see what happens when you force this hardware reality into decentralized finance.
You see, blockchains run on a zero-tolerance law called deterministic execution. This is the unyielding foundation of all decentralized consensus. It literally means that thousands of independent machines, run by different people on entirely different continents, must independently run a transaction and arrive at the exact same post-transaction state. Not similar, not close enough, the exact bit-perfect state.
So, let's walk through what happens when we invite our FPU gambler to a blockchain. Say a smart contract processes a heavy floating point calculation. Step 1, node A, which happens to be running on an Intel chip, chops off the 23rd decimal bit and rounds the number down. But then step 2, node B, running on a totally different ARM processor with different microcode, rounds that exact same number up. Step 3, absolute chaos. This isn't just a minor glitch. Computer scientists call this IEEE 754 non-associative rounding. In blockchain terms, it means cryptographic consensus shatters. The network instantly forks, putting billions of dollars at risk. Literally.
That brings us right to the climax of our investigation in Section 4, the Stylus WSM restriction. How exactly does Arbitrum Stylus handle this doomsday scenario?
Well, the answer is brute force. Arbitrum implemented a specialized compiler called Wavium.
During activation, Wavium actively scans your code. If it detects even a single native floating point instruction, it immediately aborts the deployment. And it gets way trickier, because standard Rust libraries, like Serde, for example, can actually generate floating point instructions silently in the background. So your code compiles fine at home, but Wavium catches that hidden FPU gambler and permanently locks it out. No exceptions.
Now, what's really interesting here is what happens if you desperately need floats and try to bypass this. You might try soft float emulation, basically forcing the software to do the work instead of the banned hardware. But look at these benchmarks. A basic addition operation natively in Stylus integers costs about 1 to 2 gas. Emulate that in software, the cost explodes up to 25 gas. That's over 120,000 ink in Arbitrum's metering system. Division shoots up to 150 gas. Trying to bypass the restriction completely destroys the blazing fast efficiency that Stylus was built for in the first place.
All right, finally, Section 5, the ALU surveyor solution. If we can't use the FPU gambler and software emulation is way too expensive, what's the fix?
Developers have to embrace the ALU surveyor. The path forward requires a fundamental shift in mathematical philosophy. Devs must entirely ditch continuous Euclidean curves and floating point trigonometry. Instead, they have to do the painstaking work of building exact algebraic rings. They have to literally translate those smooth continuous curves into strict pixelated grids where liquidity is mapped using exact whole numbers. They have to rely strictly on the undeniable logic gates of the ALU.
So you might be asking, how do they handle fractions without floats? Well, they use massive scaling factors. A super common standard is WOD scaling, which multiplies values by 10 to the 18th power. It's a huge number. By using these massive integers, developers mimic decimals entirely inside the integer-only ALU surveyor. Yes, it's a lot harder to program, but it guarantees absolute universal consensus across the network.
At the end of the day, building decentralized finance isn't just about raw speed at the cost of accuracy. True forensic accountability requires a foundation of undeniable truth. By aggressively blocking native floating point math, Arbitrum Stylus really isn't stifling innovation, it's enforcing reality. It's actively rejecting the FPU gambler to guarantee that the ledger remains absolutely verifiable, predictable, and immune to non-deterministic drift.
The transition from the EVM to WASM is unlocking incredible power. But as we've seen, it's also forcing us to reckon with the physics of computing itself. We just can't take our hardware's shortcuts for granted anymore. Which leaves us with this final provocative thought to ponder as we continue to push the boundaries of on-chain engineering. If code really is the new law, are you willing to settle for a microchip's best guess, or will you demand a perfect mathematical blueprint? Thanks for joining me for this explainer, and definitely keep questioning the systems you rely on.